Welcome to part 1 of the video tutorial series that will focus on carbohydrates. This series will do a brief introduction and then we'll jump right into the monosaccharides, the simple sugars. Let's get started. Alrighty, so carbohydrates are polyhydroxyaldehydes and polyhydroxyketones, or compounds that yield them after hydrolysis. So this is really referring to the simple sugars, the monosaccharides. And then in future tutorials, we'll look at how they link together. And that's where this second part of the statement comes in. So at this point, you're good at recognizing aldehydes and ketones. So go ahead and circle them in these two monosaccharides. We recognize here is the aldehyde, and there is our ketone. And then we see the many hydroxy groups, right, or alcohol groups. Okay, we're going to come back to these squares at the bottom of the page. Alrighty, so if we look closely at these two sugars, we can count the atoms and get their chemical formulas. And we'll notice that they both have the chemical formula C6H12O6. And we know that they're also, sugars are called carbohydrates. So looking at this basic chemical formula, I think it's pretty easy to hypothesize where we get the term carbohydrates. We see that there's a common factor of 6. And so if we simplify, we end up with CH2O, right? So there's the carbo, and then we have the hydrate. So the empirical formula, or the smallest ratio of the atoms in a sugar, is CH2O. Alrighty. Now, okay, as we've looked at all, as we go through every topic, there's always a bunch of vocabulary to sort out. So, as with carbohydrates, some important terms. So the primary thing is to recognize that carbohydrates are classified by the number of simple sugars bonded together. So a monosaccharide is just another way to say a simple sugar. Right, and then just recognizing carbohydrates and sugar are synonymous as well. And so then, pretty straightforward. A di would be two sugars bonded together. And then oligo, that has, depends on whose book you look in. The definition tends to go from 3 to 10 sugars bonded together. And the reason why this comes up is we'll see that sugars often act as receptors or markers as part of other biological molecules, and they come in these short chains. And then we'll look at the polysaccharides, which is where we have more than 10 sugars. And don't get too caught up on the numbers here for oligo and poly. It really varies on the source, so there's no consistent agreement. So we can see that sugars can either be aldehydes or ketones, so these words should make sense, right? If the sugar contains an aldehyde, then we can call it an aldose. And if the sugar contains a ketone, we can call it a ketose. And then biologically, most of the sugars that we're going to be interested in have either 5 carbons or 6 carbons. And so these are some prefixes that we've seen several times throughout the course. And so they have their same role. And then the other thing to keep in mind is we can take the aldose and the ketose and the pentose and the hexose, and we can mix those together to describe carbohydrates. So let's go back up to those two carbohydrates we were looking at and use these terms to characterize them. So in case you're curious, the actual name here is D-glucose, and we'll get into that very soon, and this is D-fructose. So those would be their common names. But the classification then is we would see, obviously this is going to be an aldose, and then if we count the carbons, 1, 2, 3, 4, 5, 6, right? So we would describe this as an aldose. hexose. And then the fructose, we see 1, 2, 3, 4, 5, 6. We would describe it as a ketohexose. So there are some examples of how to use those terms. Alrighty, and now that's our introduction, so we'll move on to monosaccharides. There's quite a bit to talk about there. So the first thing that we need to understand is that when we're first introduced to the monosaccharides, the simple sugars, we see them in their Fisher projection. We've been introduced to that before, where the horizontals are the wedges and the verticals are the dashes. And sugars do exist in this form. We refer to this as like the open chain. However, they like to undergo a reaction with themselves, right? So we've learned about conformers, and we see all of these tetrahedral carbons, and we know there's bending and rotation there. And then we look here at our carbonyl carbon, and we know that that is trigonal planar. And so what happens is this alcohol group right here, the hydroxyl group coming off of carbon 5, notice that we can turn this on its side and bend it around, and here is that same oxygen on carbon 5, and here is our carbonyl carbon. And what happens is they can undergo a reaction to form a ring. So here's our original carbonyl carbon, and there is the oxygen coming off of carbon 5. So the carbonyl carbon, notice here it has a double bond to a single oxygen. Here the carbonyl carbon has 2 single bonds to oxygen. So once the carbonyl carbon has taken the form of the ring, it's now called the anomeric carbon. And so it's important to recognize the relationship between the carbonyl carbon and the anomeric carbon, that they're one in the same. Now, a consequence of this planar geometry on the carbonyl is that when the oxygen comes in, it could come in from the bottom, or it could come in and react from the top. And so we'll look more closely at this consequence later, but for this example here, I'll just point out to you that the alcohol must have come into the top because this oxygen here was poked down. And when the alcohol group is pointing down, we refer to that as the alpha position. So we'll come back to this later, but let's look at a few more things about the monosaccharides. Now, the first thing is that this is the Haworth projection. So this is the most frequently used form that we'll see for the ring form. However, we can see the chair form, so don't let that psych you out. And it's important to remember, right, that the sugars are constantly going back and forth between the open chain and the rings. So here we have the same example. There's our carbonyl carbon. Now it's called the anomeric carbon. We see the alpha pointing, the OH pointing down, and that's the alpha. But then, as we mentioned, from this trigonal planar geometry, the reaction could go the other way. And so if we notice here on our anomeric carbon, right, the carbon that's bonded, the only carbon in the molecule bonded to 2 oxygens, we now see that the alcohol group, the hydroxyl group, is pointing up. So when it's pointing up, we refer to it as beta, and when it's pointing down, we refer to it as alpha. Sometimes, depending on your source, we can see the ring form written as glucose or glucopyranose. So that's another thing that just as you're doing your studies, different people will use different degrees of information. So with a 6-membered ring here, we could have the pyranose, or you might see it just as glucose. Really, the pyranose and the alpha are both telling us that the sugar is in the ring form. So it's a bit redundant, and that's why some people leave it off. If we see the alpha or the beta, we know we're talking about the ring form of the sugar, not the open chain. And the same would be here in the beta form. We could simply call this beta D glucose. And then with fructose and ribose, they will form 5-member sugars. So sometimes when you see their name, you will see it as the furan. So for example, this sugar here we could say is D-fructofuranose, or simply just D-fructose. So from now on, I will be using the simpler names, but the use of the furan and the puran, I just wanted to make sure you were aware of that so it didn't throw you for a loop if you're reading something and wondering about that piece. Okay, so now let's take a closer look at the anomeric carbons. There we go. Right? So that's the carbon atom that's bonded to 2 different oxygen atoms, right? So in the open chain, right, it's the carbonyl carbon. So remember, right, the anomeric carbon, formerly known as the carbonyl carbon, it's always going to have the lowest possible number. So for aldoses, right, that's going to be really easy. For aldoses, then it will be the number 1 position. But for ketoses, right, then it will be the number 2 position for the molecules that we'll be working with in this class. All right, so remember that we're always, we want to stay with the longest continuous carbon chain. So be aware of that. And then just to really emphasize the difference here, right, the beta anomer is where the hydroxyl group points, points up. And so one way to think about this is if you like to enjoy cocktails, you could think bottoms up, right? So the beta, so bottoms up. So when the OH is up, a more wholesome idea would be to go butterflies. Butterflies fly up in the air. So that'll help us remember that the beta anomer goes up. Alpha is then the opposite, right? So the OH group points down on the anomeric carbon. And then I don't really have a bottoms up counterpart, but ants, right? Ants are on the ground. Ants are down low, right? So ants are low and butterflies are high. So if that helps you, great. If not, no worries. Okay. So now let's look a little more closely at this reaction to help you understand what's happening, right? So the main focus here is our carbonyl carbon is going to become the anomeric carbon. So keeping that consistent, and then recognizing that it's the alcohol group on carbon number 5 that is going to react with the carbonyl carbon to close the ring. And so I really liked this figure because it really stepped us through very carefully, right? So we show that we roll over, and then I think, I tend to think of this group right here a bit as like the flagpole, all right? So this is what what I'm talking about as the flagpole, that little branch coming off. Another important thing to really notice about this diagram, well, let's keep going, right? So then here's carbon. Carbon 5 has the alcohol, and so we've talked about how it can go from the top, right? It can react from the top, right? Or it can react from the bottom. And so that leads to the 2 different anomeric carbons. And the other thing that I wanted to point out in this part of the notes is that you can think about timber turning to the side. So notice any of the alcohol groups that are on the right, they will point down. And then this alcohol group on the left, notice that it points up. So one of the skills that you want to have for this chapter is you want to be able to take a Fisher projection and turn it into the Hayworth. And so right now we've been focusing on the ring structure, but it's also important to notice the positions of the hydroxyl groups. So remember that hydroxyl groups on the right will point down in the Hayworth, and hydroxyl groups on the left will point up. And then here is our flagpole. That this is basically an R group coming off of our ring. And then the last piece then is to finish these names. Let's say which one is alpha and which one is beta. So here we look at this example and we see the OH group is pointed up. So that would be the beta anomer. And here the hydroxyl group is pointed down. So that would be called the alpha. And then let's look a little more closely here. We've been introduced to the idea of chirality, right? So remember that a chiral carbon is a tetrahedral carbon, right? Bonded to 4 separate groups. And maybe different is the best word to use there, 4 different groups. And so if we look at these anomeric carbons, we can see they're bonded to a hydrogen, a hydroxyl, a very busy carbon, and an ether oxygen. So yes, anomeric carbons are chiral. Okay, so let's look at a couple more consequences now of the opening and the closing of the sugar ring. So on the next page, we'll look at, we'll start with our D-glucose, a really important sugar that we use for energy. And the important thing here is to recognize that this is an equilibrium process, right? So we've talked about equilibrium before. So the straight chain is constantly opening and closing, and it's going in both the alpha form and the beta form. For glucose, the beta form is the preferred form energetically. My guess would be it keeps these 2 hydroxyl groups away from each other where there's some electrostatic repulsion. But anyway, the main thing to know is that if you go into the lab and you have a pure sample of one of the anomers and we mix it with water, within an hour we have a mixture of all 3. Right? So just remember that this is an equilibrium process. And we like to use the word, right? It's dynamic equilibrium. So this opening and closing, it's like giant jaws. Alrighty, so let's see how you do recognizing your anomeric carbons. Go ahead and point some arrows there. And remember that that we can just ignore the puranos. So we could just call this alpha D-glucose and beta D-glucose. Okay, and so then we've already talked about this, is just remember that this is a dynamic equilibrium process, and don't get psyched out by the words furanos or puranos. Alrighty, now let's take a closer look at the monosaccharides that you're going to need to know for this course. So there are a ton of them out there. You're not going to have to memorize them all, but there are, there are 4 that you're going to want to know. So let's take a look at those. And we'll talk about why we need to know them. So glucose, first of all, it's the most widely occurring, and it's our major energy source. So it's definitely an important one to know. So when we're writing them out, it's an aldose, so we can put our aldehyde, And then we have the flagpole at the bottom. All right. So there's carbon 1 and there's carbon 6. So now we'll put the 4 carbons in the middle. 1, 2, 3, 4. Okay. Now, in nature, D-glucose. They're all going to be D-glucoses, and that means that this bottom OH is always on the right. So we can go ahead and number the rest of the carbons, 2, 3, 4, 5. So for D sugars, the alcohol farthest from the carbonyl will always be on the right. And in nature, that's the way nature makes sugars. Now, we want to put in the remaining sugars. So we got to memorize them. Well, to me, memorizing is kind of drudgery, and so I think of it like marching. And so if we march along, right, left, right, we have D-glucose. And then the other side are just the hydrogens. Now, to make this in a ring, it could be really helpful. I think we'll try to put some green in here. We want to distinguish the alcohol group coming off of carbon 5. Because remember, that is the oxygen that's going to close the ring. So, we know that this sugar is going to make a 6-membered ring, so we can go ahead and draw that out. And then, remembering that one of the 6 atoms is the oxygen coming off of carbon 5. So, here is our carbon 1, 2, 3, 4, 5. Oh, and then here is our flagpole. So I tend to just draw it like this, a little less detail than on the previous page. Alrighty, so we've taken care of our carbon chain. Here is our anomeric carbon. Now we've been asked to draw the alpha, right? So ants are down low. We put the hydroxyl group down low. To be clear, I'll just put the hydrogen poking up. Alrighty, now remember timber, so all of the hydroxyl groups to the right are going to point down. So when we get to carbon 2, the hydroxyl group is on the right, so it points down. When we get to carbon 3, it's on the left, so it points up. And then carbon 4 is down. We've already taken care of carbon 5, and carbon 6 is our flagpole. So this is the skill that you want to bring to quizzes and exams, is that you can go from the straight chain to the ring. So we'll practice that a couple times so that you feel confident. Galactose is another sugar that you want to memorize. It's widely distributed in plants and pectins, milk sugar, and it's another important biochemical sugar. Now, the important thing to notice about galactose is it's a C4 diastereomer of glucose. Now, this term I will define for you very soon, but the main thing to keep in mind is the only difference between glucose and galactose is carbon 4. So once we've memorized the structure for glucose, we just have to know, oh yeah, galactose, we just switch carbon 4. So we'll go through the whole process again to make sure you feel comfortable with it. So we have our carbonyl carbon, and we'll have the 4 carbons in the middle, and then there will be carbon 6, our flagpole. So there's our carbonyl carbon, carbon 1, 2, 3, 4, 5. Oh, and might as well count 6. Okay, so remember, it's always going to be a D sugar. So the alcohol group on the bottom carbon always goes to the right because it'll be a D sugar. And then we're going to march along, right? But carbon 4 is where we have the difference. So now it's going to be left, left, right. So we've successfully drawn the structure for galactose. And we'll go through the process again. We're going to make a it's going to form a 6-membered ring. The alcohol group on carbon 5 comes in to close the ring, reacting with the anomeric carbon. And so here, we'll go ahead and number our carbons. 1, 2, 3, 4, 5. And here's our flagpole coming up. That would give us our 6 carbons. So we've taken care of our carbon backbone. This time, we were asked to draw beta, right? So butterflies fly in the sky. So we'll put our OH group up. Just to be clear, we'll show the hydrogen down. And now we'll look. So carbon 2 is on the right. It points down. Carbon 3 is on the left. It goes up. Carbon 4 is on the left. It also goes up. So there we go. We now have shown the interconversion of galactose from the open chain to the ring. Alrighty. So fructose is another important sugar for us to work with. And it's worth taking some time to go through the process one last time with fructose because it's a ketose. And so that shows up a little differently. So let's practice that one together. And then at that point, you'll all be experts. Alrighty. So remembering, so fructose is a ketose. And I think we've all heard of high fructose corn syrup. It's also found in honey and table sugar as part of the disaccharide sucrose. Alrighty, so this is a little different because now we're going to have 2 flagpoles. Because we have an alcohol at the end of the chain, and then we have our ketone. So then we'll only have 3 branches coming off, and then we'll have our second flagpole at the end. So this is where we have to pay attention to the numbering, right? We want to number the full continuous carbon chain. So the carbonyl carbon is now at carbon 2. Right, so it's still going to be D-fructose, so that bottom hydroxyl group is always on the right. And now we can use our glucose model, right? So we're going to march along, right, left, and we're done. So for me, it was just really helpful. Once I knew glucose and then I could refer everything to glucose, it made things simpler. So if that works for you, awesome. Otherwise, come up with your own technique and share it with me so I can help other students. So it's still going to be the oxygen coming off of carbon 5, but now it's reacting at carbon 2. So we end up with a 5-membered ring instead. So here's the oxygen coming off of carbon 5. It's going to react with carbon 2, 3, 4, 5. So I'll go ahead and number these. So here's our anomeric carbon. So this is carbon 2, 3, 4, 5. So we have quite a few carbons missing from our Hayworth projection. So if we look, what else is coming off of carbon 2? Well, we have a flagpole. So we can put this up here. And then we have, coming off of carbon 5, we have our other flagpole. So now we would have our 1 and our 6. And then I knew to point, so this flagpole we have to pay attention because we have the alpha anomer. We know to put our hydroxyl group down because ants are on the ground, ants are low. So for the alpha anomer, we put the alcohol group down, and then the CH2OH group, our flagpole, points up. For the rest of the alcohols, right, when we get to carbon 3, we see it's on the left. If it's on the left, it points up. If it's on the right, it points down. So there we go. We have finished the structure for alpha D fructose. So at this point, we've been through the process several times. So for ribose, I'm not going to go through it so in such detail. Ribose is a big deal because when we get to DNA and RNA, ribose is an important component. It's also found in ATP and coenzyme A. So ribose is the typical sugar, and so here we could describe it, right? There we see the aldehyde, so we could describe ribose as an aldo, right? And then we look at the carbons, 1, 2, 3, 4, 5, right? So it would be an aldopentose. And so for ribonucleic acids, we have the traditional sugar where we have all the alcohol groups. Notice for DNA, it's deoxyribose, right? So it means, right, 2-deoxy. So we lost the hydroxyl group at carbon number 2. And so lo and behold, right, if we look here, 1, 2, 3, 4, 5, when we look at carbon 2, now we see that it lost its hydroxyl group. So this will be the 5-carbon sugar derivative that we see with DNA. Sugars are very fascinating. We just barely get to scratch the surface. So here is our buddy glucose, and we can compare it to, if you hear about like gluconate, yeah, sorry, I got tongue-tied, right? Notice here is our flagpole. We can see that we can oxidize that sugar, or notice that we can take, right at that carbon 2 position, we can substitute it for an amine or an amide. So there's glucosamine. People take that for their joints, or N-acetyl beta-D-glucosamine. So from the sugars, we can take our functional group reactivity and learn about other ways to convert the sugars. Okay, well, this was a long tutorial, but we covered a lot of really important information. So it'd be a great idea right now to take a few straight chain sugars and convert them into the Hayworth projections and practice working with the alpha and beta anomers. Good luck.